Hi, my name is Haris Jalani, and this is my Lab 5 for Physics 2211, where I cover the physics of a falling slinky. In this lab, I use motion analysis to see if the bottom of a slinky truly stays stationary while it is falling from rest. The fundamental principle I use in this lab is Newton's second law. Overall, what I did in this lab was I analyzed a YouTube video of a man who dropped a slinky from rest, focusing on the motion of the bottom point. I used GlowScript and Tracker to both model and analyze the data and see if the bottom truly remained motionless, and if so, under what conditions it was motionless for. My results were that I found that while the slinky was still stretched out during its fall, the bottom was truly motionless. However, once the slinky had coiled back to its rest state, then the bottom of the slinky began to move. This was because of the forces of tension and gravity, as well as drag. There's a few fundamental principles and equations that I'll use in this lab. Firstly, we have Newton's second law, which states that a force is equal to a mass times acceleration. Below, you can see the two primary forces acting on the spring while it is still uncoiled. The force of the spring, which is F, is equal to kx, where x is the displacement of the spring from its rest state, and k is the spring constant, and F gravity, which is mg, or mass times gravity. To the right, you can see a short model of the forces acting on the spring. While it's uncoiled, you have tension and gravity, and the velocity is 0. After the spring coils up, the magnitude of the velocity is greater than 0, and you have drag and gravity. Here you can see the tracker model simulating the motion of the bottom of the slinky. Here is the GlowScript code that I used for this lab. I used Lab 2's code as a model. I changed the mass to 0.208 kilograms, which is the average mass of a slinky. I changed the position vector to the initial position of the slinky, and the velocity vector to 0 since it starts from rest. I found B to be equal to 65, which I used the guess and check method to find. To the right, you can see the two while loops that I used. One of the while loops covers the time period while the slinky is still coiling up, and so the bottom is at rest, and the other while loop covers the time after the slinky has fully coiled and the bottom is moving. You can see the definitions of gravity, the tension force, and the drag force, as well as the velocity and position update formulas. To the left, you can see the resulting graph from the GlowScript model. To the right, you can see the resulting graph from the Tracker model. The left graph starts constant, and once the bottom starts moving, the graph falls with a slope of negative 0.1773 meters per second. The right graph also stays constant, and once the slinky starts moving, the slope falls by negative 0.1740 meters per second. As you can see, these values are very close, meaning that the model very closely simulates the actual motion of the slinky. Any errors can probably be attributed to human error, such as my not perfectly positioning the center of mass of the slinky, or a slight difference in the actual value of the drag constant and the modeled value of the drag constant. To fully understand the lab, let's ask some follow-up questions. Firstly, did the bottom of the slinky truly stay motionless? Yes, we can see in both the tracker analysis and GlowScript model that the bottom of the slinky stays fully motionless until the slinky has coiled up. Once this happens, the bottom of the slinky begins to move downwards with an acceleration that's slightly less than that due to gravity. So why did this happen? Well, when the slinky is first dropped, since it starts from rest, there's two forces acting on its bottom, gravity and tension caused by the spring force. These two forces are equal and oppositely pointed, so because there's no net force, the bottom stays motionless. However, once the slinky is fully coiled back to its rest state, then the tension force from the spring force is gone. Thus, the gravitational force begins to pull it downwards. However, there is still a drag force pushing it upwards, which is why it moves with a velocity slightly less than that of gravitational acceleration. So, if the slinky had initially been thrown with a downwards velocity, then the bottom would be constantly moving downwards, regardless of the fact that the tension force and the gravitational forces cancel each other out. It would begin to move with its initial downwards velocity, which would decrease due to the force of drag. However, the bottom would not stay motionless in this case. As we can see, Newton's second law was very important in this lab. Because there's two equal and opposite forces acting on an object with constant mass, there is no net acceleration, because F is equal to ma, and F net is equal to the sum of all forces acting on an object. This allows the bottom of the slinky to stay at rest. Even though our intuition might tell us that it's supposed to fall, we can see that because the forces are equal and opposite, there is no motion from the bottom of the slinky. There are some potential sources of error, as I mentioned before, such as miscalculation of the drag constant or the center of the mass being in the wrong place for the tracker model. Overall, this experiment has some very useful information. You can see the effect of Newton's second law and drag, which is useful for scenarios such as a person falling with a parachute.